In this video, we take a look at the law of sines, which is a tool that can be used to solve non-right triangles. At this point, we know how to solve any right triangle regardless of what information we have about the triangle. We can use some combination of the Pythagorean theorem, the 6 trigonometric ratios, and the 3 inverse trigonometric functions to relate the 3 side lengths and the 2 non-right angles of our triangle to each other. When it comes to non-right triangles, there are 2 basic rules that can be used to solve them, the law of sines and the law of cosines. Sometimes both of these can be used on a given triangle, but often only one can, depending on what information we're given in terms of the sides and angles of the triangle. In this video, we focus on the law of sines and looking at where it comes from and also how it is used. To derive the law of sines, we're going to start with any triangle with angles A, B, and C, and side lengths lowercase a, b, and c, which are opposite the appropriate angle, like we see here. Notice that this triangle is not a right triangle because angles A and B are acute, and angle C looks to be obtuse. In order to derive the law of sines, what we're going to do is we're going to introduce a height to this particular triangle. And so I'll draw that as a dotted or dashed red segment here, and we'll call that length h. Now, if I focus on this triangle here, this is a right triangle. It has angles A, part of angle C, and then the right angle down at the base of our triangle. And we can see from that blue triangle that the sine of angle A is going to be the opposite side length, which is the height h, over the hypotenuse, which is b. We can also look at the other right triangle on the other side of our original triangle. And again, we have this green right triangle, and we can look at the sine of angle B. Using this triangle, we see that the opposite side there is h, and the hypotenuse here is a. So the sine of B is h over a. We can then solve each of these by multiplying both sides by the number in the denominator. So on the left side here, we can multiply by b to see that b sine of a is equal to h. And also for the green equation, we can multiply by a to get that a sine of b is equal to h. Well, now we see that both of these equations are equal to h. And so we can set these two expressions that are equal to h equal to each other, since they have to be equal to the same third number h. And so in particular, we see that b sine of a is going to equal a sine of b. Now, if we divide both sides of this equation by the number ab, the side length, the product of the side lengths a and b, we see that here on the left side, the b's will cancel, and on the right side, the a's will cancel. And so what we're left with is the sine of angle A divided by the lowercase a, side length a, and that must equal the sine of angle B divided by the side length B. And this is part of the law of sines rule. It says that the sine of an angle in the triangle divided by the opposite side length is equal to the sine of the second angle divided by its opposite side length. Now we could repeat this same argument by turning our triangle so that a different side was the base and repeating our derivation here. And we would see that in addition to this, we would also get the sine of angle C divided by side length C would be equal to these two expressions. And so these three expressions being equal to each other is the law of sines. So our formal statement of the law of sines is this. Given any triangle, emphasis on the word any, given any triangle with angle measures a, b, and c, and opposite side lengths lowercase a, b, and c, we get that the sine of angle A divided by A, the sine of B divided by B, and the sine of C divided by C are all equal expressions. Notice that the numerators are all the signs of our angles, capital A, capital B, and capital C, and the denominators are these opposite side lengths, lowercase a, lowercase b, and lowercase c. In practice, at a given point in a problem, we would likely only use the fact that two of these are equal to each other, but we could use any two of them. So for example, we could use that the sine of a over a and the sine of b over b are equal, or we could use that the sine of a over a and the sine of c over c are equal, or the sine of b over b and the sine of c over c are equal. It really depends on what we're given and what we know at that point in the problem. In particular, notice that in order to use any of these, we do need to know an angle and its opposite side. So for example, we might need to know angle A and the opposite side length lowercase a, or the similar statements for angle and side length B and C. One important note with the law of sines is that depending on the angle measures and side lengths that we are given, it's possible to have one triangle, two triangles, or no triangles at all that satisfy our initial information. And so it's always going to be important to check whether we have a single or possibly a second triangle that match our given information. So let's take a look at an example using the law of sines. Let's suppose we want to solve the triangle with side length A equal to 3, side length B equal to 2, and angle A equal to 40 degrees. First off, notice that we have both values for A, both the angle measure and the side length. And this indicates that the law of sines is going to be useful to use because one of the expressions in the law of sines we have completely in terms of numbers using these values for lowercase a and capital A. So for example, we might start this by pointing out that the sine of capital A over lowercase a is equal to one of the other expressions. And the other expression here, since we know side length B, should involve that side length. And so we'll use sine of angle B over lowercase b, side length B. We can substitute in the three given values, and we'll see that we only have one unknown in this equation. So this is really the sine of 40 degrees divided by 3 is equal to the sine of angle B, which is the one piece of information here we do not yet know, divided by 2. And so we can solve this for sine of B. Sine of B we obtain here by multiplying by both sides by 2. And so we end up with 2 sine 40 degrees all over 3. And we can use a calculator here to compute 2 sine of 40 degrees over 3. And that's going to be approximately 0.4285. Now, one thing to make sure here is that your calculator is in degree mode in order to get this value. If your calculator is in radian mode, then this will compute sine of 40 radians, which is a different number. Our next step is to use the value for sine of B to find angle B. Your instinct might be to use the inverse sine function, and that is what we're going to do. But it is important here to notice that there's actually two possible angles with a sine equal to 0.4285. Right? So in order to find the two angles with the sine of B equal to 0.4285, we're going to first use the inverse sine function. So we'll call this B1. And so this will be the inverse sine or the arc sine of 0.4285. And again, using a calculator, we'll see that this is approximately 25.37 degrees. Again, the calculator needs to be in degree mode for this to be computed properly. And so this angle B1 is 25.37 degrees, and this angle will always work as long as it's defined. In this case, we know we have at least one triangle in this particular problem, and angle B would be 25.37 degrees in that particular problem. We also have to remember that there is an angle in quadrant 2 with the same sine value as the angle B1 found here. And in order to figure that out, we need to find the quadrant 2 angle whose reference angle is 25.37 degrees. And we can always do that by subtracting that angle from 180 degrees, which is the complete half rotation. And so our possible second angle here is 180 minus 25.37 degrees, which is 154.63 degrees. Right. Now, angle B1, as I said, will, as long as that angle is defined, will always work. But we don't yet know about the second angle B2. We actually have to check to see whether this is possible or not. And in order to check to see if it's possible, what we're going to do is we're going to add together the two angles that we already know. Given at the beginning of the problem, we knew that A was equal to 40 degrees. And so if I add A and B2 together, this would be 40 degrees plus 154.63 degrees. And the actual sum here, it's actually easy to find, but it's not really that important. What's important is that when we get this number, we see that this is greater than 180 degrees, which is the angle sum for any triangle. And so if B2 were a possible angle in a triangle, then what we would have is two of the angles adding up to something more than 180, and that's impossible. And so since this sum is bigger than 180, this tells us that angle B2 is not going to work, and that we're only going to have one triangle for this particular example. Now, if these two numbers had added together to give us something less than 180, then we would have to look at getting both, using both triangles. However, in this case, only one triangle will be possible. And that triangle will have an angle B that's equal to 25.37 degrees. All right, now that we know two of the angles, we know A is 40 and that B is 25.37, we can always find the third angle by subtracting those two known angles from 180 degrees, which is the sum of all three of them. So in this case, when we subtract 40 and 25.37 from 180, we obtain angle C to be 114.63 degrees. And so we have angle B here, and now we have angle C. And this concludes all three of our angles since angle A was given. We also know side lengths A and B. Those were both given, and so the only piece of information left to find is side length C. And to do that, we'll use the law of sines once again. So one option is to take the sine of A over A equal to the sine of C over C, and substitute in the three values that we know. We know capital A is 40 degrees. We know that side length A is 3. We know that angle C is 114.63 degrees. And we do not know side length C. That's our last piece of information. And so we can, from this, we can, if we need, solve for lowercase c. So this will be, if we do cross multiplication, for example, we'll see that sine of 40 degrees times c is going to be 3 times the sine of 114.63 degrees. We divide by sine of 40. And use a calculator to see that C, side length C, is approximately 4.24 units long. And this will be the last piece of information of our triangle. We now know all three side lengths and all three angle measures, and we have completely solved the triangle.